So this is a turbulent kinetic energy model. This is a one equation model wherein we will be having one transport equation for the closure. So the transport equation will carry this turbulent kinetic energy as the variable. So for this model, we will invoke whatever we have learnt earlier. So first we will bring turbulent viscosity, which is nu t. We usually write this as velocity scale times the length scale. So u star is the turbulent velocity scale, L star is the turbulent length scale. We have seen one more model, it is mixing length model. So in mixing length model, we use this L star as mixing length Lm. In simple shear flows, this u star becomes Lm dou u by dou y. This implies this velocity scale is locally determined by the mean velocity gradient. In particular, if you see, this u star will become 0 wherever you find dou u by dou y as 0. Also, you might find contrary circumstances wherein this dou u by dou y can be 0, but u star is non-zero. So those kinds of circumstances also will exist. So these circumstances, if you see, it might exist in example cases like decaying grid turbulence, or you can find the center line or the axis of round jet. Independently, Kolmogorov in 1942 and Prandtl in 1945, they brought that it is better to base the velocity on the turbulent kinetic energy. It can be mathematically written as u star equals c turbulent kinetic energy power half, wherein the c will be a constant. Here this k is turbulent kinetic energy. If the length scale is considered to be a mixing length, then we have this nu t equals this constant turbulent kinetic energy power half, then mixing length. Here in this, the constant c will be approximately equal to 0.55 in the log law region. Here this k must be known or estimated, which means we have to have one equation to determine the value of k. Hence we will be proposing one equation model, that is one transport equation for turbulent kinetic energy k. So what are the components that are going to be inside this is, so let me write as components it is like 1, you have the mixing length, it is Lm of space and time. 2, model transport equation for turbulent kinetic energy, again function of space and time. And third, the turbulent viscosity, which is C k power half L suffix m. And fourth is the Reynolds stress, which we are arriving from turbulent viscosity hypothesis. Then we have this Reynolds equations, which we will be using to solve for u of x comma t and p of x comma t. So having said about the model, from the specifications, of Lm, solutions of exact and model equations, the following fields are determined. This is U field, that is velocity, pressure, mixing length, turbulent kinetic energy, turbulent viscosity, and Reynolds stresses. Our main aim is to now write a model equation for turbulent kinetic energy. How can we write this equation? Is like dk by dt, the total derivative, so dou k by dou t plus u dot del k, which is equal to minus del dot t dash plus capital P minus epsilon, wherein this t dash is half of ui dash uj dash uj dash plus ui p dash by rho minus 2 nu u suffix j dash sij. Now what you can infer from this is the total derivative, temporal derivative, advective derivative, this is the transport, this is the production, this is the dissipation. In this equation, now we have this dk by dt and this production term capital P, which are available in closed form. This epsilon, that is the dissipation, and this delta t dash, these are all unknowns. How you can find these unknowns? It is by modeled equations or closure approximations. We also should note that at high Reynolds numbers, this dissipation epsilon scales as u naught power 3 by L naught, wherein this u naught and L naught are the scales of energy containing motions. So it is especially saying the turbulence scales or the energy containing motions, which is giving energy to the fluctuations. Now this epsilon is modeled as epsilon equals c suffix d k power 3 by 2 by L suffix m, where the c suffix d is a model constant. Examination of this in log law region yields CD equals small c power 3. To eliminate this mixing length Lm, we will invoke this new t and then substitute these above things. We will get a small c capital CD k square by epsilon, or nu t epsilon by k square equals c capital D. For simple shear flows, we have this k epsilon and this nu t, which is equal to minus u dash v dash by dou u by dou y. Now what we can do is, we have this term for epsilon, but we didn't find any term for t dash. So for t dash, what we will do, we will use gradient diffusion hypothesis. Hence this t dash can be modeled as minus nu t by sigma k del k, wherein this turbulent Prandtl number for this turbulent kinetic energy, this sigma k usually is taken as 1. So this diffusion and turbulent viscosity will be equal. Now considering this t dash, epsilon and other terms, we will substitute this in the original model equation for k. We will arrive at dk by dt equals del dot nu t divided by sigma k del k plus production minus epsilon. Here this nu t is c k power half L suffix m, epsilon is cd k power 3 by 2 divided by Lm. In 1993, Wilcox performed experiments and found that this one equation turbulence model gives modest results when compared to mixing length model. So there are certain drawbacks, and that is the length scale Lm, which needs to be specified. If you want to supply boundary conditions when you're practically implementing these kinds of model, you need to provide the values of k in the inlet, and in outlets one might use zero gradient boundary condition to solve the governing equations. For wall boundary conditions and related boundary conditions can be applied. For other boundary conditions, one can refer to the reference books, wherein they would have specified what kind of boundary conditions you can apply when you are coming up with special boundaries.